Yeah, let me know. But okay, very often we are going to be working over linear codes, which are just vector spaces over the final field that we are working on. Every single vector space has a basis. If we collect the basis elements for our code, we can create a matrix associated to the code, which is a generator matrix. The rows of my generator matrix will create the entirety of my code. Another matrix that is important for every single code is the parity check matrix. All that happens is that I multiply the matrix times the code words and I obtain 0. And the row space of my generator of my parity check matrix will generate the dual code, which is another code that is associated to every single one of my codes. That one, of course, is also a vector space, it's a linear code. One very classical strategy to solve this error correction problem is the Ruiz-Solomon codes. What we do is the following. We take a finite field, and from there we are going to collect some evaluation points A1 until AN, and then we are going to be taking every single polynomial that has degree at most k minus 1, where k is the value that I have decided to take for the dimension of my vector space. Actually, k is the total number of digits that I want to be able to transmit so that the receiver corrects and recovers the original information. So k is how many I want to send, but n will be the actual length of the messages that I send with the redundancy included. So very often, I mean, to make it useful, k will be smaller than n. So if we evaluate all those polynomials, we obtain the Ruiz-Solomon code, which is a linear vector space. It is a linear code. Notice that I have used polynomials that are actually very beautiful. The same polynomials we have been working since, I don't know, elementary school? Or, I don't know, middle school, probably, depending on you. I don't know. Middle school? Okay, middle school. I buy that. And they're super cool because they're commutative. They are an Euclidean domain, principal ideal domain. And if I want to find the value of a polynomial at a point, all that I need to do is just go and plug in and do the operations, and that's it. On the other hand, when I was in second year of PhD, I got introduced to something very scary. SQ polynomials. So the SQ polynomials are very similar to the regular polynomials. Like if you see a SQ polynomial in the street, you will say, well, it's just a regular polynomial. However, they have something very weird going on. The way in which we define the multiplication is like this. X times one number is not going to be A times X. Instead, it's going to be sigma of A times X. And in here, sigma is an automorphism. So this structure is no longer commutative. The product of two polynomials cannot be made in any single order. I mean, you need to be very careful. Also, it's not unique factorization domain. And to evaluate one SQ polynomial is a little bit painful. It's not going to be enough to go and plug in. Like for example, in here, with this polynomial x squared, if I just go and plug in alpha, I obtain alpha squared. But this factorization in here would tell me that the real evaluation should be 1, not alpha squared. So in this example, we can see that it's actually not a evaluation is not just done by plugging in. And well, SQ polynomials were giving me a little bit of a headache. And all of a sudden, we came up with an idea that was, okay, let's study nonlinear codes. And in particular, we wanted to study these nonlinear Ruiz-Solomon codes. They are very similar to the Ruiz-Solomon codes that I told you about, that I told you that they were linear. However, there is something that we have changed. I am thinking that I have FQ as subfield of FQM, and I will take the evaluation vectors, the evaluation points still in FQM, but the coefficients of my polynomial for the evaluations are only in the small field, only in FQ. This way, the code is no longer linear in the sense that they are not FQM linear. They are only FQ linear. We have lost a little bit of linearity. And well, notice also that I have used the regular polynomials. I didn't put the sigma over there, no skew so far. However, a little bit of thinking made us realize that if I take this cyclotomic coset to be the evaluation points, then turns out that my code that was created using the regular polynomials is actually an FQ linear skew cyclic FQM code. Well, that is a lot of things in just one sentence. What is that? Well, a FQ linear skew cyclic FQM code, we have in here the definition, is to start with a FQ vector space of FQM to the n, but also it has this invariance property that what happens is that if I have this code word, I want the shift by one position and application of the automorphism in every single entry, I want that resulting code word to also be a potential message that I can send. So if I take this evaluation vector, then I obtain that my Reed-Solomon code that was looking very commutative with the evaluation points, I mean, with the coefficients being in FQ and polynomial being superregular, turns out that the word skew is appearing now.
So this definition depends on, it just depends on fixing an automorphism. Is that the same thing with multiplying the skew? Like,
yes, I fix the automorphism. Yes, I mean, I will take the automorphism, and in this case, well, actually, if you want the result, in here you should be applying the correct automorphism to create your cyclotomic coset. So usually we want that our automorphism to cover the entirety of the cyclotomic coset. So yeah, we want every single one of them is h to the q to the s. So we want the s to be co-prime with m. But okay, so turns out that because of that, I put attention back to this kind of codes, FQ linear, skew cyclic, FQM codes. So I would like to understand how do they look like? How does every single FQ linear, skew, FQM code look like? And for that, I want to step a little bit back and talk to you about cyclic codes. A code is cyclic if the shift of the code words by one position is also another code word. So that's pretty much what is going on in here. And what happens is that if I have a cyclic code, I can take every single code word and think it like a polynomial. So pretty much what happens is that if I have this code word, then I will use them as the coefficients. That's a bijection between the Cartesian product of FQ to the n and the polynomials in FQ, commutative so far, modulo h to the n minus 1. And also what happens is that my cyclic code under this map gets becomes an ideal. And these ideals are, well, this is a principal ideal domain. So it will be generated by one element, which will be the one with the smallest degree in the code. Also, what happens is that all of this is motivated. I mean, actually, the proof that is behind being an ideal is the following. If I multiply h times one regular polynomial of them, I obtain the shift. Like the last coordinate move to the beginning, and all of them move one position. So this is classical results. Every single cyclic code can be understood like a cyclic ideal, generated by one element. But we are going to have something similar, but to study the FQ linear, skew cyclic, FQM codes, we are going to be using these two rings. Rn is the skew polynomials modulo h to the n minus 1 with coefficients in FQM, and Pn is the skew polynomials with coefficients in FQ modulo h to the n minus 1. So I can define this other map phi from the Cartesian product to the ring Rn by making use of polynomial representation. Again, I take the entries of my vector, and they will become the coefficients of my polynomials. And if I do that, then I can notice that any FQ subspace is an skew cyclic code if and only if the image under this map is a Pn submodule of the ring Rn. So instead of thinking about a code having the property, the long property of invariance, I will instead think on trying to identify how do every single Pn submodule of Rn looks like. The proof of this theorem, some essential part of that is this product in here. If I multiply h times one representation of a regular code word, then I have h times c0 plus h times c blank, and whenever I do the shifts by positions, I want to put the coefficient in front, I obtain the sigma in front. I have the sigma in every single one of my coefficients, and also in the last one, I have h to the n minus 1, which means that that becomes a number 1. So that sigma of Cn minus 1 moves to the front. So that's the motivation for these codes. So I want to understand how these Pn submodules of Rn look like. And well, turns out that we have this result. What happens is that every single one of these codes, I can write them like the direct sum of these cyclic modules. And you will say, well, you just told us that you just jumped a lot. Let me explain you how we did it. But I think the easiest way to understand what's going on is by making one example. So I want to take this example, C equal to P4 times this generator. So that will be one element that will generate every single one of the elements of the submodule. The elements of C look like a polynomial in P4, that is a polynomial of degree at most 3 with coefficients in F2 times the log polynomial generator in here. So I am working with the basic, I am working with F2 as a subfield of F16. So I want to understand how does this P4 module is looking like. And for that, what we do is the following. First of all, we obtain a normal basis, alpha cubic, alpha to the 6, alpha to the 12, alpha to the 9. And that is a basis of F16 over F2. And so that we can make this decomposition in here. And I will be using this decomposition for the following. I will take my generator and I will write it like a polynomial with coefficients 0s and 1s times the basis element, 0s and 1s times the other basic element, and so on. And those polynomials with coefficients 0s and 1s are going to be used into the next matrix. Again, here is the decomposition. And I will place every single one of these entries over the first row. If I had more generators, I would have added more rows to my matrix. In this case, I have one generator, so that I only need one row. The other rows are the elements that fall into, all of these are generating the ideal generated by h to the n minus 1. So what happens is, I forgot to mention all that. I have this pi. What this pi is doing is that it takes skew polynomials over F16 and will do the canonical projection into R4, which is now this polynomial's modulo h to the 4 minus 1. And I want to understand how does the preimage of my code is looking like. So I want to understand this preimage, and this has two parts. One part that is essential to describe the code, and another one that is the repetition, every single multiple of h to the n minus 1. So with this first part, we generate the essential part. With the another one, we are obtaining the repetitions. But every single one of these rows will help me to generate my preimage. Then I have my matrix, and I will apply the Smith normal form. What it does is that it will obtain two matrices, S and T, so that if I multiply them by the sides, I obtain this diagonal matrix. This this diagonal matrix, I will call the entries HI, and those will be total divisors. Right now, you can think of them divisors. They will be divisors of the next one, but also all of them will divide h to the n minus 1, so that I can find this di that multiply with the hi are going to be equal to h to the n minus 1, and I can also commute them. In general, I will be able to commute di and hi. Then I will also use the matrix T that I had. I will find the inverse, and I will use the row vectors of the inverse, because those generate the skew polynomials to the power m. And then I use these TIs, multiply them with the elements of the diagonal of the semi-normal form, and those HIs times TI will generate the preimage. And also, I will use later the DI for something. But, actually here, the DIs times my vectors of CIs will be generating the ideal generated by h to the n minus 1. So I have this to generate the entire thing, and this to generate the repetition. So what we do is the following. If I want to understand C, well, turns out that C is equal to every single thing that falls into the code divided by the repetition part. But I have found basis elements for the preimage. The CI is a basis for the preimage, and I also generate the h to the n minus 1 with the DI-CIs. With third isomorphism theorem, I can cancel out the CIs, and I have the direct sum just of these cyclic modules. And that's how we can obtain the composition theoretically, and we can also do it numerically. There is an implementation in Python that, well, I uploaded to my GitHub to be able to solve this problem. You know, like you give the matrix, and then with the entries over skew polynomials, and then it will make the Smith-normal form, and that will give you what elements do you need to use to find the decomposition. Also, we had that I have an FQ vector space, not FQM. What will happen is that if I take the dual, that will be FQM linear. So the dual of the dual will be FQM linear. So what I have is that the dual of the dual is not equal to the original code. However, if I redefine an inner product in this way, I take two elements that are skew polynomials to the power m, and I make A times t and B times t. That's a new inner product. Then I will obtain an inner product that will allow me to define this other dual. I mean, these CI primes are using the DI times TI. Meanwhile, the CIs were using the TI times the HI. So under this inner product that we have defined using the decomposition, we obtain this result. If I take one element from the code and another element from the dual, the inner product is equal to 0. And also, now I obtain that the dual of the dual is equal to the code, not like happened with the regular one. Well, in this case, this was on over FQ linear codes. We can also do it in more general intermediate linearity, and we can also obtain the same results. Here, the good thing about this is that we are using h to the n minus 1, and this is an element that is in the center of the skew polynomials. But here is again what I have mentioned before, and with this I will be concluding. This is an open question. I want to be able to describe FQ linear skew constant cyclic codes, and the difference in here is that I have this constant A instead of 1 as I had before, and now happens that h to the n minus A is not an element of the center, so that this technique is no longer working. So we need to find something different to be able to solve this other problem of being able to decompose the codes as direct sum of cyclic modules. So yeah, that's all. And if anyone wants to work over this, well, I expect your emails. Thank you. Thank you. Yeah.
So this is, are you saying you somehow like have generalized these Solomon read codes to like a new setting? I mean, is this expensive to implement? Has this theory been implemented? Like, what's the advantage of using these, I suppose?
So,
as opposed to like the Solomon read code? Is this
okay, so what happens is that, I mean, it's currently being researched if these codes can help to construct quantum codes. So in general, the study of nonlinear codes is with that direction, to try to make constructions of quantum codes. Thank you. Thank you.